We want to take a look at solving inequalities involving absolute values symbolically. So we're solving symbolically, which means we want to complete the algebra that goes along with it. Our first absolute value, we have an absolute value of negative 0.5x plus 5 is less than or equal to 2. Now, if you remember a rough sketch of what an absolute value function looks like, this absolute value function should have, let's call it, a bounce. If we want to be less than some specific value, we should be looking at the portions that are below that value. So for the case of less than or equal to a number, we're going to be bounding this. We're going to say that that negative 0.5x plus 5 should be less than or equal to 2 on one side. Also should be greater than or equal to negative 2 on the other. Keep in mind, the reason that we have that three-part inequality is we know we have to have some value inside the absolute value. That absolute value symbol will make it positive. So we want all values between that negative 2 and that positive 2. We have a three-part inequality. If we were solving the left or the right side, we're just going to take a look at the center. X is the variable where the action takes place anyway. So in order to isolate that x, I could subtract 5. And that's what I will do. I will subtract 5, but from all three sides of our inequality. So we will have negative 7 is less than or equal to that negative 0.5x, which is less than or equal to a negative 3. Again, action is on the variable x. It's being multiplied by negative 0.5. So I will divide by that negative 0.5. But not just the middle, all three portions of our inequality. What happens when we divide by negative numbers? Signs change. That's a fact of life. Negative 7 divided by negative 0.5 will give me a positive 14. Negative 0.5 divided by negative 0.5 will give me just 1, so I will have 1x. Negative 3 divided by negative 0.5 will give me a positive number, positive 6. But because our signs changed, all of our signs change. That 7 went from negative to positive. This less than or equal to symbol will also change, becoming greater than or equal to. Negative 0.5 divided by negative 0.5 became positive. This less than or equal to symbol will also change and become a greater than or equal to symbol. And our negative 3 divided by a negative 0.5 did become positive. Notice all the signs changed, all, including the inequality symbols. Of course, it would be better to write these in a proper form. Generally, we will write the smallest number to the left. But you know, if 14 is bigger than x, that means x has to be smaller than 14. If x is bigger than 6, that means 6 must be smaller. And so we have our inequality written from least to greatest. Or we could write this in interval notation. X takes on all values starting at 6 and going to 14. We did have equality here. The original symbol was less than or equal to, so we will have a bracket on the 6, less than or equal to, so we will have a bracket on the 14 as well. And we have our solution. Taking a look at our second inequality, we have the absolute value of negative 0.5x plus 5 is greater than 4. And again, just taking a look at a rough sketch, absolute value bounces. If I want to know when it is greater than some value, well, I'm talking about above some value. So we're looking at some area to the left and some to the right. This problem we will break up into two separate linear inequalities. Our argument, negative 0.5x plus 5, could be greater than 4. This would be the area that goes to the right on our graph. Or we could have negative 0.5x plus 5 be less than negative 4. And that would correspond to the area on the left of our graph. So we just have two separate inequalities to solve now. Solving the one on the left, I can subtract 5 from both sides. That means my negative 0.5x is now greater than negative 1. I will now divide, because I'm multiplying by a negative 0.5. I will divide by a negative 0.5 and try to look surprised when my signs change. That negative divided by a negative became positive. Negative 1 divided by a negative 0.5 becomes a positive 2, and because signs change, all the signs change, including the sign of my inequality. And so I found part of my solution, x is less than 2. Of course, we did have the part that was screaming on the other side, but again, I'll solve it the same way. I could still subtract 5 from both sides of this inequality, so we'll have our negative 0.5x less than a negative 9, and dividing by that negative number, negative 0.5, we will have x. Negative 9 divided by negative 0.5 is a positive 18. All my signs changed from negative to positive, and so our inequality symbol will also change. We have all values where x is to the left of 2, x is less than 2, or x is to the right of 18. X is greater than 18. And again, we could write this in our interval notation as well. All numbers to the left of 2, those would be the numbers starting at negative infinity and going to 2. Negative infinity will always carry a parenthesis because we can never equal negative infinity. Because our inequality did not have an equal to part, it was strictly less than, we will have a parenthesis at 2. Or we denote with a union. All numbers to the right of 18 are the numbers that start at 18 and head on to infinity forever. Parenthesis at infinity, we can never equal infinity. But also we did not equal 18. Since we did not have equality at 18, we will have a parenthesis there as well. So our interval notation, all values from negative infinity to 2, or from 18 to infinity, and we're done.